Today's topic is machine learning with Python. It's quite obvious from the title that we are going to be discussing machine learning and we are going to be discussing Python as a programming language. Before we start, allow me to introduce myself. My name is Faisal Aziz, and Python programming is probably my favorite programming language. Not probably, actually it is my favorite programming language. Number one, because of its simplicity. It's so easy to learn. And there's very little that I cannot do with Python. Moreover, when it comes to the world of machine learning or artificial intelligence, hands down, Python is most likely the best choice. It's very versatile, and it can pretty much do whatever it is that I need it to do. So suffice to say that this is one of my favorite topics. Previously, I was discussing about data structures and algorithms, and I said that that was one of my favorite topics. And the reason is that it helps me become a better programmer. And my best programming work is usually done with Python. So then what is this course about? Well, today's session is a very beginner level course, but despite being beginner level, I do assume a certain level of technical knowledge. Because this course will not only deal with theory, but also with hands-on practice. What I shall attempt to cover is the basics of machine learning, just to be able to understand what it is. A quick overview of Python. Of course, we cannot have a Python tutorial over here because that itself is a much longer course, but I will touch on it. Then we shall see how we can use Python to implement some machine learning. We will have theoretical coverage of some machine learning models. I quite often abbreviate machine learning as ML. And also some terms relating to the subject matter. And I will use a high-level explanation of some of the models, but of course, needless to say, I will not be able to go deep. And there is going to be quite a lot of hands-on work. You may choose to follow along. That will be beneficial if you can just follow what I'm doing. And what this course is not. Well, this is a technical course, which means it's not a simple follow-along course. There shall be coding, which means that it's not going to be just hearing only. This is not an observation-only session. I shall not go deep into any kind of specific algorithms for machine learning. I will not be teaching Python from scratch. You will not be required to install anything. No installation is required for this. There won't be any assessment, of course. So I am going to be making some assumptions over here. And one of them is that you have a Google account, because I'll be using Google Collab for programming, which means that I can just use the browser, but you will need a Google account. Google account meaning your Gmail is good enough. So I recommend that if you do want to follow along, sign on right now to your Gmail, and then later it'll be much easier to start working with Collab. This course is not going to make you an expert. Okay. I'm assuming that you understand the basics of data structures and algorithms. you do have some programming experience, because of course we cannot learn programming from scratch, uh, and that too for machine learning, and that you have a Google account, as I mentioned previously. You don't have to be a Python expert, but at least I expect, or it would be better if you at least know what Python is. You could actually not have any of these, and you could still understand this course. Yes, you could do that, but the technical implementation might be a little bit challenging for you to grasp. If you want to make the best of this course, ask me questions and try to follow along. There is going to be a recording for this, so you can always pause and cue back and check what it is that I'm doing. So the topic being machine learning with Python. Let's try to understand what machine learning is at first. When we talk about machine learning, generally we talk about two kinds of machine learning. There's supervised learning and unsupervised learning. Although there are other kinds of machine learning, but that would go beyond the scope of this course. So I will limit my talks to supervised learning and unsupervised learning as far as machine learning is concerned. So what is machine learning? That's the first thing that comes to our learner's mind. Well, we know what programming is. From data structures and algorithms, we got a glimpse of what programming is. Programming is instructing the computer to do something. Usually it involves writing code. And you prepare the computer for a certain set of events, and it works within those parameters, such as, say, your browser. Someone programs this app, which is a browser, whereby its domain of working is you can enter an URL or website address, and it will go there. Once you're in the website, it relinquishes control over to the web app, but it will make sure that there's a secure connection, that there are encryption protocols in place, and these have been programmed. Quite often you will see that these browsers, they need to be updated because some new security threats have been discovered, and the programmer programs patches. So these are codes or instructions that the programmer codes and then updates your system. And the reason they have to do it is because they observe new situations and equip the browser to handle those new situations. The same thing happens with your app. Any app that you have on your phone, it goes through periodic updates, either for security or to be compatible with the new Android or iOS that you have, or to add new features. So you have to manually program these and then push it onto the marketplace or app store from where the updates take place. So this is a manual process. The app itself cannot grow. Unlike a human being, whereby just observing something, by observing something, you can learn. For example, say you have never ridden on a maglev train, okay? But if you just see how people are lining up and boarding it, you'll be able to understand it. So what you observe, when you see many people doing it, you tend to follow. That's data. So using that data, you see a pattern of behavior and you know how to copy it. That's what machine learning is about. Okay? It checks the data, reads the data, tries to observe a pattern from there, and learns from that data. Meaning, if you implement machine learning algorithms, you don't have to do programming all the time. You just have to give it data, which we generally term as historical data. And the computer will learn from that data. In a nutshell, that's what machine learning is. Now, there are two major machine learning algorithms, which deals with supervised learning and unsupervised learning. And in order to see it in action, I'm going to be using Python. Again, not just because it is one of the easiest programming languages to learn, but also Python seems to be the language of choice by data scientists to implement machine learning algorithms. So now, excuse me. What is this supervised learning and unsupervised learning? Well, supervised learning uses what we call labeled data to predict a label. What is label? Label is generally an outcome. If the label is continuous, it's called a regression problem. If it is categorical, it's called a classification problem. In the data structures and algorithms part, we discussed a little bit about this, about continuous data and categorical data. So when I say label, it could get a little bit confusing because the terminologies used in computer science sometimes differ from how we speak. So for instance, let's take this example, supervised learning, for classification, which means non-continuous data. So the features are height and weight. Is it possible to determine someone's gender with height and weight? Perhaps it is. Let's take a look at this plot. I show you this plot, and I tell you that the purple purple plot, it represents female, and the blue one represents male. It makes sense that males generally tend to be heavier and taller than females. Okay, so it makes sense. So based on the height and weight, which we generally call features, you can detect the label, which means what are we trying to classify the data as, which is either male or female. So again, remember, the determining factors, such as height and weight, are called features. In this example, we're just using height and weight because it's easy to conceive. It's easy to comprehend. So the features are just two, height and weight. There could be multiple features. These features are sometimes referred to as dimensions. So if there were other factors to consider, such as, I don't know, it could be height, weight, and what else can there be? Height, weight, I don't know, say, what else? Anything. It could, I can't really think of anything. Talab, can you think of any other features that we could possibly use? Let's say, I don't know, for this to think of, sorry?
I mean, for male and female, other than height and weight, perhaps you can also
BMI.
Perhaps the length of hair. I don't know. I mean.
Okay, yeah, length of hair. Let's take length of hair. Okay, so I put another dimension over here, which will deal with hair length. Maybe it has some effect. So now it's in 3 dimensions. So Maybe it will help with my prediction. Maybe it will not. But what I'm trying to show you is that as we add features, it goes into a different dimension. If it goes beyond 3, it becomes very hard to conceive it, which is why I am showing you. Just 2-dimensional data. Again, how does this help? Okay, let's imagine we are doing some machine learning. You are the machine. Okay, all you have is this: height and weight, and this is the data that you see. That's all you see. Okay. Now I give a new point. This green dot. Now, do you think the person represented by this green dot is a male or female? What do you think the answer is? Do you think it is a male or a female? This green dot. This green dot. This one. Is this a male or female? Well, to me, it seems to be clustered with the male. That's one way to see it. Or the spatial distance from here seems to be closer to the blue one. See, the distance is less, where the distance from this is quite high. So if you take the average distance from this to every one of the dots, it will seem that it's the average distance between this green dot and the blue dot are much less. Even the furthest one away, which is this one, is probably less than the closest purple dot. This is most likely with this height and with this weight, it is most likely a male. So this is how generally a machine would predict it, that it seems to be a male. This is called prediction, to be able to predict. And you can do it with a variety of different kinds of data. Okay, even situations that are evolving or have not happened yet, it is possible to do prediction based on this. So this is a classification problem. Very simple, very easy to understand. This is the basic way in which machine learning usually works. But you see, this is classification. It's not continuous data. What if we had a continuous data problem, which we call regression? Yes, we could use that as well. Let's say I give you the square footage and rooms, and the label, or what you need to predict perhaps, is the house price. Of course, there are other factors as well, where the house is, what's in the surrounding. But let's take the simplest of features. What would be like? It would probably be something like this. The more the square feet, the higher the price. If I want to plot this into a line, it would be something of this sort. This is continuous data, because square footage could be a continuous increase, right? It does not have, it's not categorical. And you can make it categorical if you say luxurious or non-luxurious, but let's just assume over here that it is continuous, and it is continuous usually. So the price is directly proportional to the square feet. Although it is not a straight graph, it's slightly curved, but there is a correlation. More the square footage, greater the price. Now we only have certain points of data over here. We have, just for the sake of this example, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points. We have 9 points. And based on these 9 points, which is these 9 data whereby it was probably taken from a table where the square footage and the price was in a table of sorts like this, where you had price, sorry, excuse my handwriting, and SQFT, and these were the values given in a table. So there's been in an Excel sheet, which we are pretty accustomed to. From there, these plots were created. Now, it doesn't cover every point in this graph. Just 1, 2, 3, 4, 5, 6, 7, 8, 9. Just 9 records. Just from 9 records, this was created. However, if we were to give you a square foot, which was not plotted, you could still most likely tell me the price, right? Based on, say, what would be a price of a real estate property whose square footage corresponds to this. Well, it's quite simple now, isn't it? It's not really that hard. All you have to do is just plot the corresponding price, which is over here, whatever this may be. This is a prediction. Although this data does not exist for this square footage, but if this square footage was given, it would detect the price. Now, say you have a web app whereby you want to know, say a foreigner wants to invest in real estate in Malaysia and wants to know the price of a property of, say, 500 square meters. Okay, this is square foot, so 5,000 square feet. So for 5,000 square feet, what would the price be? But the data is not there. There is data for 4,000, there is data for 5,800, and many other plots of data. In the web app, if the user or the potential investor were to type, okay, I want a 5,000 square foot property, how much would it be? If you don't have machine learning, the system would say, sorry, data not found, or something that we don't have information. We have information for 5,800, we have information for 4,000. But for 5,000, I don't have that data. But if you were to ask a human being, a realtor would probably say something between whatever the 4,500 and 5,500 is, somewhere in between. The realtor would be able to tell you. If you were to implement machine learning in that app, the app would also be able to tell you, just with this methodology. Okay. So we have just seen 2 methods in a short span of time. We have seen we could do it this way, or we could do it the other way, which was the height and weight, where in each plot we could see what is the spatial distance between certain group, the male group and the female group. So these use 2 different kinds of algorithms. Now, in this case, this is regression. Regression is a very common methodology of machine learning, perhaps the simplest. Okay. Regression analysis, it could be linear or it could be non-linear. This is not linear, but it could be linear. I mean, close to linear if you wanted it to be. Say, I mean, if I did plot a straight curve, maybe it would be close. Just say imagine this is one straight. It would give you a pretty good approximation. This is linear, but not always there's linearity work. Okay, sometimes it may have to be a little bit non-linear, and it's up to the data scientist to see by observing the data whether you should use a linear model or a non-linear model. But a regression would work with whatever it be. A regression would work. A regression model would work, which is the case in this case. In some cases, not necessarily you need a regression model. What does a regression model do? It tries to plot a curve that best fits all the data points. That way, when you ask it a question which is for which there is no data point, it just simply gives you the corresponding prediction. So this is one way. The other way we saw was something like this, where you had male and female. So anytime you had a new point, it would measure the distance from this point to all the points, to all the blue points, maybe find the average, and maybe find the distance from this to the rest, and find the average, and see which one it is closest to. If it's closest to this, it will classify itself as this, which in our case was male. So there are many methods of doing this clustering, and the most common one is called KNN, K nearest neighbor. So regression and K nearest neighbor. These are machine learning algorithms, okay, or models. So there are quite a few. There's some called PCA. There's something called decision tree. So there are quite a few of them. And these are actually quite deep topics. So I will just touch on them and maybe demonstrate one of them to you. Okay, so now moving on. Supervised learning. Now, we have seen basically how it is. But how does it actually operate? First thing you need is data. That's the first thing you need, data. You need quite a lot of data. And it's this data from which the machine learning system will try to see a pattern. Okay? But what machine learning algorithm should you use? That's what you would know as a data scientist. Okay? If you want to learn, this is just an introductory course for you to know whether you want to go into machine learning or not. So if you go deeper into machine learning, you will be exposed to many different models, such as the regression model, such as the KNN model. The different models have different efficiency of working for different kinds of data. And as you expose this model to the data, it gets trained. Meaning, as you feed the data, it reads the data and tries to discern a pattern from it. This is the learning process. And once it's learned everything, it is now a trained model. Once you have a trained model, you may attempt to predict. But what if you don't have historical data? This could also happen, especially for clustering. Okay. For instance, the male and female, the clustering that we saw. What if I did not tell you male or female? I just told you these are human beings, and they seem to be clustered with height and weight. You could now think that, is it male and female, or is it Cambodians versus people from Saudi Arabia? People from Saudi Arabia are much taller and much heavier than people from Cambodia. Cambodians, I think, have the shortest average height. So you could think that this clustering, if it's international, probably it's segregating two nations. It could be that. It could be that. This is you as a data scientist who has to figure it out. The machine learning will just do the clustering for you, but will not tell you what it means. You as a data scientist have to interpret the data. Okay. This happens quite a lot as well. especially with demographics or behavioral patterns, the machine clusters the output, and you have to try to figure out what did it cluster it as, and that's when this is unsupervised learning, where there is no label. It just gives you an answer. And as a data scientist, you have interpreted. Okay. For instance, let's say in this case, just as I was telling you, just height and weight. It has clustered it, but is it trying to segregate the gender or to nationality or people from different socio-economic class? People, like for example, in Asia, I think South Koreans are the tallest average height. And amongst Malaysia, Singapore, South Korea, and Japan, most likely Malaysians are the shortest, and the South Koreans are the tallest. So it could be a segregation of two Asian countries. We don't know, depending on what data you're giving. How is it clustering? Is it clustering with gender or to nationalities? We don't know. Okay, it's just that we can see two clear clusters. It could be the height and weight of dogs. Okay, I have dogs and cats. Say I tell you these are the heights and weights of pets in Baikal cows. So maybe the purple ones are cats and the blue ones are dogs. Could be that. Or could be, say, the height and weight of all the dogs in my neighborhood. And then I could probably predict that these are two different species. Maybe these are the poodles and these are the German shepherds. Could be that. It's not going to give you the answer, but it's going to say predict it. So once you put a label to this, then when a new data comes, you can classify it as probably a German shepherd. So how this process works, the first thing is you need the data. The data is a gold mine for you. Nowadays, one of the most valuable assets that companies can produce is data. Companies like Facebook, Twitter, there are huge amounts of data from which they can discern behavioral patterns. Advertisers love this because they can predict what will probably sell. And how it works is, the first step is data acquisition. That is getting the data. That's the first step, getting the data. Then data cleaning. What is data cleaning? Sometimes data could be missing, could be inaccurate, could be a bit skewed to one side, could be an outlier. We have to clean this data. And unfortunately, this is the most boring part of data science. And it could take anything between 60 to 90% of your time. Yes, 60 to 90% of your time. Very boring, very monotonous. Sometimes it could just a slight mistake over here could completely mess up your entire pipeline. So you get better with experience on data cleaning. There are various methods for data cleaning. For instance, say your data has male and female. It may not best fit the model. So just as an example, I'll give you an example. Say you have a table that looks like this. Say your gender, your life expectancy, your total savings, and your amount of money you spend on medical bills. Okay? So maybe you're an insurance company and you want to see how much you spent on medical. So if this company is going to insure you for your health, this data could be very good. Now, gender is either male or female, and it seems that men tend to get sicker. Okay, they have higher savings, than females, maybe, but their life expectancy is less than females. Their savings are higher than females. So are their medical bills. For females, they seem to spend the most only when they give birth. Otherwise, there's not much expenses. So this is what the medical company is trying to predict. Okay? It's trying to predict how much your average medical bills are. So these will be the red markers. So when you're a male, it would probably charge you more. Okay? Or if maybe there's a correlation. When you have a lot of savings, maybe your earning is a lot higher. So you maybe have a healthier lifestyle. So you don't spend as much on medical because you don't get sick. So there are various factors. But the problem is maybe M and F are not the best way. So sometimes you have to do something called one-hot encoding, whereby you change this data. Instead of writing it like this, you write male and female. And in this case, male will be 1, female will be 0. These are, of course, mutually exclusive. In this case, male will be 0, female will be 1. Or you could just do 1 means male, 0 means female. It could do it that way as well. So this is where the data scientist comes in. This is actually a part of data cleaning. You may have to transform the data into this. Sometimes you need to normalize. For example, the savings. It could be 1.5 million for someone. It could be 1,500,000. Over here, it could be 300,000. You have to normalize this between a scale of 0 to 1. You may have to do that. So this is where data cleaning comes. Sometimes data might be missing somewhere. You have a choice of either predicting the data or completely deleting this data. So what you're going to do depends on your decision as a data scientist. And this just data cleaning itself is a whole course by itself. Okay. So in 2 hours, it's impossible to master machine learning, but it will give you insights on what kind of work you need to do if you do want to get into machine learning and what it might look like. So moving on. After you have the data, you go through data cleaning. After data cleaning, you have clean data. Now you have a nice table with a lot of data. This is where you do what is known as a train, test, split. A train, test, split, which means you take your data and you just split it out. How do you split it? What does this splitting actually mean? Well, say you have a long table with lots of data, lots of features, and this is your label. Say this is height, this is weight, this is the length of your hair, and the label is whether you're male or female. So what you do is, say you have 100,000 records, okay? 100,000 records. You will split it out, okay? You will straight out, split it out. Sometimes you have 30, 70 split. Some people do a 20, 80 split. Now, split is not right off from here. It's a random split, which means randomly you choose 30% of the data, very randomly. And you set it as test data. You completely remove that as test data, 30% or 20% of the data, you completely remove it out. Let's say 30%, this is the most common usually. 30, 70 is the most common. You split out the data, test data, and you forget about this. You forget that this data ever existed, okay? 30% of the data, just randomly records chosen and removed. What then? Then the remainder of the data, which is 70%, assume that this is all your data. The 70% is your 100%. Just assume that. And then you put it into the training model, which is you choose what model you will use. We have seen KNN, KNN's neighbor. We have seen regression model. I've also spoken about two more, PCA, principal component analysis. You could go for decision tree. Decision tree is something that works, in my opinion, a lot like the human mind and much easier to understand. Maybe you will use that. Whatever the model will be, you train it with that. Now, once you're happy that it has been trained properly, you evaluate. What is this evaluation? What does this mean? Remember that 30% of the data that you had set aside? Now, you bring that data back. You take this model and feed this data and let it work and see what it predicts. Now, remember, our table had height, weight, length of hair, and it would predict the gender, height, weight, and the length of hair, or whatever it be. With this, the 30% of the data, you already know what gender it is, right? But you don't show the gender. You tell the machine that, okay, you've learned it now predict it. This is the height, this is the weight, this is the length. Is it a boy or girl? And it predicts. Okay, for the next record, also tell me, is it a boy or a girl? And you keep on doing this. I mean, you don't do it manually, the system does it for you. Then you check the labels and see how much of it is correct. You compare it. Maybe you see that it predicted out of 100,000, you have taken up 30,000. It predicted 20,000 data as correct, and 10,000 were incorrect. 20,000 were correct, 10,000 were incorrect, which means it's got about a 66.66% accurate, 67% accuracy. Is this good enough? I don't know, depends on you. Is this good enough or not? So if you feel it's not good enough, again, you adjust the model parameters. So you adjust the model parameters to check. Again, you test it and see if you're happy or not. Now, this process can go on and on and on. Sometimes you may realize that the model that you chose, maybe the model that you were using is KNN, and it's not the best model. Okay, so you try with a different model, maybe decision tree, and you still see that you're not really happy. Maybe your data is not clean, so you have to go back again. This is a very frustrating process sometimes. You have to keep on doing this and doing this and doing this. It's not like in the Hollywood movies. You're typing and things are happening and there are beeps and sounds and things coming from flashing. It's not like that. It looks more like this. Looks more like this. Yeah. Your screen will more likely look like this. Okay. So it's not as glamorous as it may seem in the movie. Okay. So again, this is a cyclic process where you just keep on evaluating the model, you find mistakes, you adjust the parameters, and then again you train the model. And you keep on doing this and keep on doing this and keep on doing this. And finally, when you see that your test model is good, you should keep something called a holdout model, which means, remember we kept 30% out over here. Maybe from 30%, take out 1/3, which is 10%. And when you're absolutely sure after your 100th try, and you're absolutely convinced, then this holdout model is where you do the final test to see whether it works or not, whether your prediction is good or not. Generally, prediction of 93% and above seems to be good. But then again, it's a subjective matter. For medical situations, maybe you need a higher prediction. So it depends on you. Okay. So once you're happy, you deploy it. You deploy the model. Once you're happy. This was a very bird's eye view of how things work in the world of machine learning. Okay? So I want to discuss this machine learning model with you, and maybe show you a demonstration of how it works. But before that, is there anyone over here who has any kind of programming experience? Anyone?
I have a very basic Python knowledge, very basic.
Wonderful. Anyone else? No? Okay. Yeah, we will be using Python. So I don't want you to install anything in your computer. We can use the browser. We can use something called Google Colab. Now, how I use it is, if you can open a window and search for Google Colab. Welcome to Collaboratory. The first response that comes, click on it, and you should come to Google Colab. Now I've opened it in incognito mode. This is why I'm not signed in. What you need to do is you need to sign in. You need to sign in. Okay? So once you sign in, you can go to File, New Notebook. File, New Notebook. And a new notebook will be open. Okay? This is what it will most likely look like. Okay, let me just separate this out and resize this for you so that you can see it all. And you have a notebook. You can actually do Python programming over here. Okay. I recommend you start a Collab Notebook and you click on Connect. Now, when you click on Connect, it's actually connecting to the Google server, and it's going to give you the resources, meaning processing power. It's going to give you memory. So nothing in your computer is actually being used. And you have Python. It's as simple as that. You have Python. Isn't that beautiful? That's Python. So let's do a crash course on Python. So Collab has cells. If you click on this code, it'll make cells for you. And each cell can have multiple lines of code. Multiple lines of code. For instance, I could write 1 plus 7. Now, I've put a space after 1. You don't have to. I'm just trying to make it look nice. Now, I can either press the play button and we'll give the answer 8, which is 1 plus 7. Or I could say 6 minus 4 and press Shift Enter. That would also work. I generally like to press Shift Enter. And it gives the answer. Just like plus and minus, you can also do multiplication. 4 times 8. And multiplication is done with the asterisk, which is common in all programming languages. And I press Shift Enter. It gives me the answer. Just like that, I could do division. I could do 8 divided by 2 and Shift Enter. And it gives me the answer. But notice that these are whole numbers, whereas this one says 4.0. Remember, we learned in our data structures and algorithms about data types. So these whole numbers are called integers, whereas the decimal number is called a float. Divisions are always floats because division generally tends to give you fractional answers. You don't always get whole numbers. Rarely do you get whole numbers. So by default, Python assumes that there is a high possibility that the answer is going to be a non-whole number So it just converts the answer to a decimal. Okay. You could, for instance, 7 divided by 2, 3.5. If you want to get a remainder, you could always do 7 modulus 2, and you'll get 1. So this is one way we usually check whether something is a whole number or odd number or even number. Any modulus with 2, if it's an even number, the answer is usually 0. For instance, let me make it 6 and press Shift Enter again, and it is 0. Notice if I press Shift Enter, a new cell gets created. For example, in middle school, we learned about parentheses. So if I were to say, write 2 plus 3 times 5 minus 1, let's make it look nice, and press Shift Enter, answer is 16. But what if I were to put brackets like so? And press Shift Enter again, answer is 20. It works exactly the way we did in our middle school. But all these calculations we're doing, it's getting lost. We need to retain this calculation sometime, which brings us to variables. What are variables? Variables are just locations in the memory to which we give a name, because memory addresses are very long and difficult to read for humans. So we just give it a name. For example, say X. I want to call my variable X. So X is a memory location. And I want to put something over there. I want to put a value of 2 over there. Okay. Instead of Shift Enter, I'll just press Enter. It just increases the size of my cell. And I'll make another variable called Y. Y equals to 3. Notice it says 1 and 2. These are line numbers. And I press Shift Enter. But nothing happens. But something is happening. It's storing these values in the memory. If I make a new variable, say Z, and I say Z equals to X plus Y. And if I were to run this, it would give me something which I don't know. It's not showing me. How do I see this? Well, usually in Python, you just say print, you open parentheses, and write Z, and Shift Enter. 5, it gives me the answer. So we see that we can have variables and we can have a way to print it. Of course, this is a notebook. One great thing about notebook is not always do you have to write print. You can just write Z and it will give you it will show you the result as well. But we generally tend to use print because we don't always use a notebook. If we were able to port this into what we call idle, which is the usual Python way of doing things, then just writing Z would not work. Notebooks are special. Notebooks are great for experiments. Okay. Now variables don't always have to be one letter. You could say my_var equals to 67, and let's say print my_var divided by Z. And it gives you 13.4. It gives you the answer. So variables, it could be anything, as long as there's no space, as long as it doesn't start with a number, as long as it doesn't have any syntax, which is reserved by Python itself, such as the word print. Okay. It's not just numbers. You could also use characters. For example, my string. You learn from your data structures. These are called strings. My string is equal to I love Python. Great. Now print my string, and we'll say I love Python. You could also print it directly, of course, with either a single quote or double quote. It doesn't make a difference. So you could just say, I really like Python. Sorry, excuse my spelling. And it will print, I really like Python. And we use the print statement to print it. So we can see numerical data types and we can see string data types. Another common data type is called list. So let me make a list. I'll just call it my list. You can call it whatever you want to. And lists are always in square brackets. And you could put a list of things separate by comma. For example, 51, comma, 0, comma, my name, comma, 78.986. No, let me put something 3.1415. 426. Okay, let's keep it 3.1415. Okay. So we've got an integer, string, float, and enter. So if I were to say, what is my list? It gives the answer. I could take out each element. Each item inside the list is called an element. And elements have a placeholder. They're called index. An index starts from 0. If I were to write my underscore list 0, it would return the first item in the list, 51. If I were to say I want this, Aziz, so this is the third element. So since it starts from 0, you have to get the third element, you have to write 2. Because 0 will give you the first, 1 will give you the second, and 2 will give you the third. There you go. So now we've learned another data. Again, remember, we're not here to really learn Python. I'm just showing you what Python is like. If we have some experience in Python, it would definitely help you a lot. Okay. So now we know that computer is all about logic. Yes and no. 0 and 1. True or false. So that also constitutes a data type in Python, as with most other programming languages. And it's called Boolean data type. It is either true or false. For instance, is 3 greater than 5? No. If I were to write this, it would say false. Is 3 less than 5? Yes. It says true. Okay. What about is 4 plus 3 divided by 6.98 greater than 3.14 to the power? Okay, to the power you write with this. To the power 3. Let's see. I don't know the answer. Okay. Okay. Here's the problem. Just unsupported operand. So sorry, to the power I made a mistake. Sorry. Double star. Okay, false. Because just this double star means to the power. Sorry, too many programming languages in my head, and the answer is 30.959. So it's a pretty long number. So this is bigger than this number. Let's check. Is it actually bigger? Let's see. Yes, this is 4.429, whereas this is 30.959. Of course, this is greater. Of course, this is greater. So, so this statement is false. If I were to reverse it and run it, then it's true. This is called Boolean. Okay, this is called a Boolean. And we use this for a lot of things, especially for conditions. For example, this is true. So let me just copy this, and if I were to write if, well, this column, then print this statement is true. Okay. If it is not, then else print this is not true. If I write it, what will it say? This statement is true. If I were to change it, it says this is not true. This is called condition. Okay, this is called a condition. And this is where logic comes into play. This is where programming starts to get life, where you can actually check and do something. Okay, you can actually check and do something. Okay, there's also something called loop in Python, where you can use the same condition to iterate, which means to go through a lot of conditions. And the most common one is called for. So let's take this list we have. This list, my list. So a for loop will go through this list. So I can write for I in my list. What this means is go through my list, and every time you come across an element, put it in a variable called I. And then what? Well, then do whatever I ask you to do. I ask you to print. I ask you to print I. And it will print. Every time it just goes through, it keeps on printing an element from I. Once it's done, it exits. This is called a loop. This is the most commonly used loop. There are other loops like do, but we're not going to go into the while loop, called the while loop. We could do the same thing with a while loop, but we don't use it that often. And since this is not a Python programming language, I'm not going to go into it. This is just to expose you to what Python programming looks like, because I'm going to be using Python to demonstrate a certain machine learning algorithm or operation. So now, when we talk about machine learning, one of my favorite machine learning algorithm is decision tree. Why? Well, because it, in my opinion, seems to mimic the way human brain seems to work. Okay. So let's take a look at this. Okay. Now, clear your mind. I know what I've been saying all this while may seem a little bit confusing, but it was mostly theoretical, so it may seem a little bit confusing. But let's see it actually how the machine really works or thinks. And if you try to perceive it from a very simplistic point of view, it might be easier for you to comprehend. So let's see what this decision tree is. Again, it's a machine learning model. Okay. So again, something off Wikipedia I took. A decision tree is a decision support tool that uses a tree-like model of decisions and their possible consequences, including chance event outcomes, resource costs, and utilities. It is one way to display an algorithm that only contains conditional control statements. Again, when you take formal definitions, I find myself left with more questions than answers. So let's take a more realistic approach. Okay? And I will use a true case, a real case. Okay? This is my dog. It's a husky, and her name is Chloe. I just gave her a bath today, and it started raining. I got dread. So, being a husky, Yeah, I have a dog and 4 cats. It needs to go for a walk or a run. And my son takes care of that each. And my son is 11 years old. And he loves the dog. He loves the cats as well. He loves animals. He takes the dog out for a walk. Sometimes I take the dog out for a walk as well. Only if it's a holiday. Otherwise, I don't. I take the dog out for a walk if it's a holiday. Today was a holiday, a weekend, but I did not take the dog out to walk. Why? Well, it's raining outside right now. I don't know if it's raining where you are, but where I am, it's raining. I guess on most places in Kuala Lumpur now, it is raining. So today is not the day I would take the dog out for a walk. Now, my son, he's a very analytical person. He is top of his class in mathematics and all that kind of stuff. So he analyzes everything, every behavior, and he likes to classify everything as yes or no, if possible. And he's really an analytical. So what he did is he made a chart that looked something like this. What is this? Well, it has the days. He has classified the days, okay? He hasn't put Sunday, Monday, Tuesday. He just classified the days as either weekend, a weekend or weekday. Okay, weekend or weekday. So this is a weekend, this is a weekend, this is a weekend, this is a weekend, this is a weekend. So 1, 2, 3, 4, 5. It's a much longer table. I'm just showing you that these are the weekends. And the rest are all weekdays. Now, if you notice, these are the days I did not walk the dog. Didn't walk, didn't walk, didn't walk, didn't walk, didn't walk, didn't walk, did not walk the dog. And what's common is that every single day that I did not walk is a weekday. Wait, this is a weekend as well. Okay, this is a weekend. Did not walk the dog. This is a weekday, 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 weekday. I did not walk the dog. I walked the dog. Okay, I walked the dog. And I walked the dog these 2 days. So looking at it, can you see a pattern from here? Any pattern? Do you notice anything from here? As a human, what do you notice? Anyone? Well, what's quite obvious over here is that, well, I walk it on a weekend. 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 But this weekend, this one weekend, I did not walk it. What was so special? The rain. Yes. When it rains, I don't walk. It could be cloudy, sunny, doesn't matter. It's the weekend. If it rains, I will not walk the dog. So in your head, you can set up a condition. Right? If I were to write a software, you could write the software. If you were to write a software, how would you write the software? Well, you would categorize. When do I walk the dog? When don't I walk the dog? I do walk the dog when it's a weekend, when it's sunny, when it's cloudy, overcast, I walk the dog. When do I not walk the dog? It's a weekday if it's raining. If any of these conditions are met, that it's either a weekday or if it is raining, I shall not walk the dog. Right? I shall not walk the dog. So the programming logic would be like this. Is it a weekend? No. Okay, then don't walk the dog. Is it a weekend? Yes. Great. How's the next question? Is it raining? say yes. Then don't walk the dog. Okay. Is it raining? No. Then walk the dog. Why? Because we're already in the weekend section. So this is the basic logic. And this is called a decision tree. This is called a decision tree. And this is something that actually works. This is actually something that works in machine learning. Okay, so this is called a root node, the base of decision tree. Then there's splitting. See, it splits out. It's raining, not raining. And these are leaf nodes, and this is the decision node. Okay. There's something called pruning as well when you want to shorten this. What do you mean shorten this? What are you talking about? It's pretty simple. Yes, it's pretty simple because we've already seen a pattern. That first question they ask is it a weekend and is it raining? These are two main questions. Or you could just ask, is it raining? And then is it a weekend? It will give you the same answer. Okay. So one has to be yes, the other has to be no. But what if you could not see the pattern and you did an inefficient splitting? For example, you first ask, is it cloudy? That's the first question that you ask. And the answer is no. So then is it sunny? No. Okay. Is it raining? No. Okay. Is it a weekend? No. Okay, then don't walk the dog. This is a pretty long way. So now what if it was a cloudy day? Or is it a weekend? Yes. Then walk the dog. Is it raining? Yes. Don't walk the dog. Is it sunny? Yes. But then again, you have to ask me, is it a weekend? If it's not, don't walk the dog. If it is, then walk the dog. What if it's a cloudy day? Okay, irrelevant. Is it a weekend? No. Well, then don't walk the dog. But if it is a weekend, then you have to ask, actually, you don't have to ask whether it's rainy or not, because it always says it's cloudy. Now, this is far more inefficient than the previous one. So sometimes you have to do pruning, which is reduce the steps. But how many conditions do I get for walking the dog? 1, 2, 3. 3. How many conditions, how many times does it result for not walking the dog? 1, 2, 3, 4. 4. 4. So this is not an efficient splitting. And the machine learning algorithm has a way of calculating. Because you might ask, how in the world will the machine know whether to first ask whether it's cloudy or not, or whether to ask whether it's a weekend or not? Because the machine does a calculation. And the calculation, there are two ways of doing a calculation. One is an entropy calculation, another one is a Gini calculation. I generally tend to use the Gini calculation, whereby I try to purify the condition. What in the world does that mean? What is the Gini calculation? Well, over here, how many possible outcomes are there? 1, 2, 3, 4, 5, 6, 7. 7. Of which 3 of them are walking the dog and 4 of them are not walking the dog. Whereas if I take the previous one, there are 1 to 2 conditions where I don't walk the dog and 1 condition where I do walk the dog. Okay, whereby it's a weekend and it's not raining. Okay. Of course, there's another one that it's a weekday and it is raining, in which case it would be a no. So there would be another condition which I have not put over here. So let's see how this actually works. The calculation that one would do for this is, let me just show you a Gini calculation, how it's done. Okay. I'm just going to give you a very simplistic example. Okay? It's raining and not raining. It's a weekend and this is a weekday. Okay? Weekend and weekday. Okay. Now, it's raining. It doesn't matter whether weekend or weekday. Okay. I'm not going to take the dog to walk. Now, it's not raining. It's a weekday. Will I take the dog to walk? No. It's not raining. It's a weekend. Will I take the dog to walk? Yes, I will. So a Gini calculation, you don't get intimidated. You don't have to do it yourself. The computer does it for you. The formula is G of Q for all sets of data Q, a summation of, it looks like this. It's not really that complicated. 1 minus 2. So this is the calculation. If I were to do it like this, how many conditions of red are there that I don't take the dog to walk? Okay, that I do not take the dog to walk, the crosses. How many conditions of crosses? 3 of 4, right? 3 of 4, 1 minus 3, which is times 1 minus 3 over 4. Okay, which comes to 1.875. What about if I wanted the calculation of the times I do take the dog to walk? Well, exactly opposite of this, right? There's only 1 over 4, 1 of 4, times 1 minus 1 over 4, which gives me the exact same answer, 1.875. So this plus this together comes to 0.375. Now, the idea is to get the lowest score, because Gini calculation is something like this. The highest being 0.5, okay? Which means it's a really bad split. So that's the worst that can happen. We don't want this. We want to reduce it. Whereas if I took the previous one, remember there were 4 reds and 3 whites. Okay, if I were to do this calculation, then what I would probably get is, instead of, let me just change the color to blue. What I would get is, instead of 3 over 4, I would get, hold on, let me just do the calculation myself. Okay, so number of crosses I got was 4, number of ticks I got was 3. So in total, it was 7. If I were to do a Gini calculation for the class of not taking the dog to walk, would be 4 over 7 times 1 minus 4 over 7. 1 minus 4 over 7, that is 4 over 7 times 3 over 7. That is 12 over 49. 49. And for the times that I would take the dog out to walk, it would be 3 over 7 times 1 minus 3 over 7, which is 3 over 7 times 4 over 7. Again, which is 12 over 49. So if you add these two together, which is 24 over 49. So let's do the calculation, which is, okay, it comes to 0.4898. Very close to 0.5. So this is a bad split. And the computer actually does all this calculation. You never have to do this. That's why I said that don't worry about it. I'm just showing you what the computer does. The computer does this calculation. So to know which is the point to split. Okay, so don't get intimidated. Don't worry about it. Okay, it's quite simple. Okay, so let me show you an example. Okay, so what I did is I took the liberty of making this code along for you. You don't really have to worry about how the code works. Just observe what I have done. Okay. What I did is I imported 4 libraries. NumPy is a mathematical library. It helps me calculate lists very easily. Pandas, this is a magic library. But there's no such thing as magic in computing. It's science, which is a library that someone has written using this NumPy, which can help me read tables and records very easily and very nicely. Okay, like Excel, databases, and stuff. And Matplotlib, well, this is to help me plot curves and graphs. And Seaborn, it just helps make the Matplotlib plots look nicer, prettier. Okay, yeah, prettier. So let me just expand my field of vision a little bit. Now I've connected it. I'm just going to run this to import the libraries. The first run takes a little bit longer. And the second thing I'm going to do is I am going to load some data. What data? It's a very common data set that is loaded, that is used in the field of machine learning. What it is a table of features of penguins. So some scientists, they went to an island and they took penguins, and then they measured the flipper length, the beak length, the beak depth, I think some other length and depth, and based on, and also then they recorded what species of penguin it was. There's chinstrap, Gentoo, and Adelie. So this is the data that was stored. Okay, this data is called penguinscreen.csv, a simple CSV file. I simply took that and I put it into a data frame called BF. Remember, we just saw how easy it is to make a variable in Python. That's what I did. In this variable, I read this. Okay, I read this file. And if you want to take a look at it, it looks a bit like this. The data file dot head. Head will just show the top part of it, okay? Or you know what, let's just make life easier. Let's not write head, let's just write DF. Okay, so it shows the top and bottom. So look at this. It says the species Adelie, it's in this island. There's a bill length, there's a bill depth, there's a flipper length, and there's a body mass, and this is the gender. So based on these, they did not predict, they actually just wrote it down. They actually measured everything and they wrote down this is this species and this is these species. Okay. Now, which is great. What I want to do is I want to create a prediction. What do I mean? What kind of prediction? What I want to do is I want to see, say I don't have some of the data. I want to see that just based on these measurements, bill length, bill depth, say someone who is not a zoologist or does not know much about penguins, but is good at measuring and measures the bill length and bill depth and sends it to me. Can I say what species this is? Can the computer predict it for me? Can the computer learn from this data, from this 332 records, from 333 records? Can it learn that if the length, breadth, width, weight is like this, it's of this species? Can the computer do that? Well, let's see. As I told you, I want to use a decision tree classifier. How will I do this? What I'm going to do is I'm going to plot a pair of graphs, okay, using Seaborn. Now I'm using Seaborn and I'm too lazy to type, so I'm just going to call it SNN. That's what I did. Programmers are generally lazy people, okay? And sadly, I'm one of them. So I'm just going to make something called a pair plot. A pair plot, whereby it will show two or more features and try to make a predict and see if I can get segregation of the species based on that. So the code for that is SNS dot pair plot. SNS has many kinds of plots. I am looking for a pair plot. In the pair plot, where is going to get the data from? Well, from the data frame. And what I want to do is, I want to separate the colors out based on the species. Wait, if I write species, how does Python understand? Python does not. It just reads this header from the data species. Okay, and sometimes it's a bit bright, so I'm just going to use a palette. I usually always use this dark 2. There are many others. Actually, you don't even have to write this palette. It goes dark 2. I like to because I know what I want. Okay, and I run this. It takes a while because it actually checks for correlations between all of them. Okay, now let's look at this. Now remember, these three, the green one is a Delhi, the orange one is Gen 2, and the purple one is chin strap. And these are the features: build length, build depth, flipper length, body mass. That's all it has. Build length, build depth, flipper length, and body mass. Now, I want to see which features actually really segregate it. For example, let's take this, flipper length and build depth. It doesn't really segregate the species because it looks like chin strap and Adele are overlapping, which means they have similar flipper length and build depth. Gen 2 is very different, okay, but not these two species. This is not a good example. Neither is this. This looks okay, but some overlap. Maybe this is good. What is this? Build length and flipper length. Now, as a data scientist, I think this is good. It may not be good, but it looks like you have very clearly segregated out. And what the features that have been used? Build length and flipper length. So I'm going to use these two features. I'm going to use these two features. I'm going to make a dummy data frame. Okay. Just to show you what the data might look like. Here's the code: pd dot get. It should autocomplete. I like autocompleting to see that I'm not making any spelling mistakes. There you go. Get dummy. Now get dummies. I'm just gonna take these two features. Okay. And what are the features? The features are the build length, right? Build length. Look at this double check. Build length and flipper length. Okay, I'm going to use these two features: build length and I don't want to make it a spelling mistake. I'm just going to copy and paste flipper length. Flipper length MM. Okay, yeah, MM. Definitely missed that out. And the syntax requires that you pass it as a list. So now, what my data would look like is just this: build length and flipper in millimeters. That's it. Now, remember we were looking at the machine learning where we have the features and we have the label. In the world of machine learning, features are usually denoted by a capital X, and the label is usually denoted by a small y. I do not know why. It's just like that. Okay. Someone who does programming will know, for when you use the for loop, you usually use the variable I. There could be many reasons for that. Okay. But like when we do algebra, we generally use X. You don't have to use X. You can use P if you want to. But people don't. Unless it's time, they don't use P. They use X. It's just a general convention. Okay. And the vertical axis is they use Y. It's just a general convention. You don't have to. But generally, people seem to do that. So I'm just going to take these two features. I'm just going to copy it because I'm too lazy to type again and again. And I'll put in a variable called x. And the y is the label, which is something that we want to know. And I will call that df.species. There you go. Okay. And now I've got my x and I've got my y. Now, whichever feature I take, the decision tree will eventually split up to contain these features. So remember this splitting into train and test model, taking 30% out randomly. It's a lot of work. But Python has libraries which can do it for you. This is one of the reasons why I love Python. There's this beautiful, beautiful machine learning library called scikit-learn. Probably one of the most used libraries there is. And I like to use that. And the scikit-learn also has ways to do the splitting for you. And I don't want to do all the coding, so I will just import that library from scikit-learn. And it's called sklearn. Okay, from sklearn dot model selection. I hope I got the spelling right. I want to import this train. There you go, train test split. So now I know that I didn't make any spelling mistakes. Great. Now the next part of the coding is very long. So generally I don't do the whole typing. What I do is I just wait for it to autocomplete. Okay, I made a spelling mistake. Instead of import, I wrote import. Okay. Train test split. So there's something called x underscore train x underscore test. It should autocomplete by now. Sometimes it takes a while. You know what? Let's just do train test split. Yeah, there you go. Train test split. Loading. There you go. So just copy this. I just copied it. There you go. See the wonders of being lazy. And I just do this. Okay. The dot means it's just going into the next slide. Now, what does this mean? Well, basically, I've got my x, it's splitting x, okay, and y into 33%. Okay, let's not make it 33%, let's make it just 30%. And random state, it doesn't mean anything. If you do this random split 42, it means the randomness of yours and mine will be exactly the same. So this is the code. Again, me programming for so many years, I don't have this memorized. I just get from autocomplete. And I recommend you do the same because coding and libraries change. So now what happens is that it automatically split it for me. See how easy Python is. It just split it into train and test. Okay. Now I want to use my decision tree classifier, what we just learned. You know, that splitting and all that we did all this time. I want the computer to do this. So from sklearn, again, from sklearn dot tree, I want to import the decision tree classifier. So you see, there are many kinds of decision tree. I want the decision tree classifier, okay? Because I find this to be quite cool. And how to use it? Remember, we first make the model. We choose our model. Well, our model is this, but I need to tell Python that this is the model I want to use. I've imported it. Now Python knows what it is, but Python doesn't know that I want to use it. So I want to use it. And I'm going to make a variable, which in Python lingo, we call it a model object. Okay. It's just a variable, but Python is an object-oriented language. So everything is an object. So this model object will have a decision tree classifier. The decision tree classifier. What this means is I'm telling Python that I want to use this model, this machine learning algorithm. Okay, that's what I'm telling Python. Okay, now that I've told Python, now I want to tell Python, okay, now you know the model, right? Okay, now you need to fit the data. So you take the X train data, which again, Python has already split for me. So I want to fit it. So model.fit X train, it should autocomplete. Yeah, X train and Y train. Not the test, the train. Train is 70% of the data. Okay, I'm telling Python to do that for me. And great, it has done it. Now, what it has done is actually, it has learned. Now, let's try to see, let's take our test data and see whether it can predict properly. So I'm going to make a base prediction. You can call it whatever you want, okay? You don't have to follow my exact naming convention. So I'm going to take the model.predict and I'm going to use the X test. Okay, I've trained it and it has made some predictions. I have no idea whether the predictions are good or bad. So I want to do an evaluation. Now, to do an evaluation, there are many kinds of metrics. So I'm going to import a lot of metrics, and I'm going to show you why I'm importing so many kinds of metrics. So again, from scikit-learn dot metrics, okay, I am going to import quite a few things. I'm going to import something called confusion matrix. I'm going to import classification report, which is actually what will make most sense to you. Classification report. Maybe a plot confusion matrix. But yeah, we don't need to all use that, but let's just import these. Okay. And okay, they've imported properly. Now let's see how good our prediction was. Print classification report. With what? Our Y test, okay, against the base prediction. Base prediction is this, which I predicted, and I have no idea whether it's good or not. Base prediction. Now, when I run it, it's going to give me some numbers. Okay, I made a mistake. Okay, can anyone tell me what mistake I made? Here, spelling mistake. There you go. Accuracy is 96%. It's actually not bad. It's actually quite good. It's quite good, which means I chose the features well. These are good features to choose. You should try it with different features. With different features. Maybe add more features, not just 2. Maybe take 10. Take more. Take as many as you want. Now, okay, but that nice if else tree that I showed you, I want to see that. Okay, you could also see that actually from, actually I should have imported that earlier. From scikit-learn, there dot tree, you can import something called plot tree, which again does everything for you. And don't get intimidated by the code. This is very standard code. I'm just going to plot a figure. Okay, PLT. PLT, remember I imported PLT, matplotlib.pyplot to plot a graph, and I call it PLT because I'm too lazy to type the whole thing. So PLT.figure, let me give a fig size. Fig size. big sign, equals to, let's say, 12 by 8. And DPI dot print. You have to experiment with this actually, because it depends on your screen size, and you have to experiment with it to see what works best for you. What works best for me may not work best for you. I've got a Retina display on a MacBook, so my one might be a little bit different from yours. So I'm going to plot it. Plot tree, which means I'm using this method or function, what you want to call it. My model. Remember, I made a model, and I'm going to make it fill, because I've tried it before, and if you don't do it fill, it doesn't look as nice. Fill equals to true. This is just decoration. And the feature names. I want to see the feature names here. Feature names, yeah. Feature names. What should the feature names be? Exactly what is in the feature list. X. We call it capital X, right? Dot column name. Again, you don't have to put this actually. Even if you don't put this column, it will still work. Okay, it will still work even without this. Okay, so yeah, let's see if it works. It did. So this is what the tree looks like. See, it does a Gini calculation. So this is how it does the splitting. This is one of the reasons why I like decision tree, because you can actually see how the machine is thinking, what the machine finds to be more important. It has found that splitting it at the flipper length is most likely more important. You can try the whole thing again without just the bill length and the flipper length. You can do that. Okay. In the x.get dummies, you can add more features. Or you could just put the whole data frame. You could just write data, all of the data frame except for species. You could do that. And you can check it out if it splits it exactly this way or not. Maybe it will, maybe it won't. So you have to experiment. And this is what data scientists often do. They try it out and see. Okay. So this has been an example and demonstration of how machine learning works. Okay. I did not program it to know what kind of combination of length and breadth and different features of a penguin pertains to its species. The machine automatically taught itself. So with any kind of data, the machine can learn. And as you get more data, the machine can learn more and more. Okay. So any questions? Anyone, any questions? No? Just for the heck of it, say we take body mass into account. Okay? I want to take body mass into account. And I'm going to put body mass over here. I want to see if it does it's better. And what I will do is I'm going to go to the beginning, put my cursor over here. I'm going to go to runtime. I'm going to say run all. And every time it runs a cell, it's going to give me a tick. And tick. I just want to see if it looks any better. So remember, I got 96% accuracy previously, okay, with just these two. Now, do I get a better one? Nope, 96%. If I look at the graph, it still determined that flipper length is probably the most influential thing over here. In fact, it looks like it didn't even consider the body mass. Looks like it. So it's pretty smart, actually, if you ask me, this machine learning algorithm. So oh wait, okay, sorry, my bad. I didn't add it. I put it in the wrong place. My bad. Sorry, let me just put it over here and try it again. Okay. Runtime, run all, and let's see. Still 96%. And let's look at the split. Flipper length, build length, body mass. Yes, there's body mass, but it doesn't seem to be affecting it much. So why take so many features when you're getting the same kind of accuracy of 96%? So the lesser features you take, the less resources it will take the computer to see discernible pattern from. When there's too much data, of course, the computer will need more resources. If you're getting the same kind of accuracy, then it seems that these two features give it more accuracy. I mean, you could try it. Let's just get rid of flipper length altogether and see what happens. Okay. Now let's see what happens. I'm going to run it all again. So which features are most influential? There's a science to it, which is called feature engineering. But again, it's beyond the scope of this lecture. But suffice to say, this is a good way to see that what features seem to separate the three species most. Now let's give it the accuracy. 94%. See, there's a drop in accuracy. So body mass is not a good feature to check. Flipper length is a better feature. If I replace body mass with features with flipper length, and let's get rid of body mass from here as well, just to avoid any kind of confusion. From 94%, you see it will probably go up again. You will not always get the same results all the time, because there's certain level of randomness. When it splits it, there's a certain level of randomness, and some records may contribute more to the learning process than others. Okay, it seems it's doing it at 94%. Build length, flipper length. Still at 94%. It did not seem to increase. But if you run it again, maybe it will. So try it out. Try it out. Sometimes, you could just add all of the features and see whether it does any better. So I've got build length and flipper length. What about something else? Build depth. Let's try to add this. Build length, build depth. Let's try to add this. Let's see if it gets any better. Build length, and I'm gonna put build depth over here, and see if it gives me any better results. This time it's just for the plotting, okay? Not for the machine learning. It has nothing to do with machine learning. It's just for our observation. Okay, I made a mistake. I added it over here. I should have added it over here. Sorry, my bad. I'm just going to put this over here and run it again, hoping to get a better result. Yes, I did. 97%. That's good. I think previously, how much did we get? 96? So 97% is really accurate, really good. Some of you might get even better results than this. So this is how machine learning works. I will conclude today's session with this. Okay.